The last one, and probably the most important one. Well, I can't really say it's most important because all three criteria need to be met, right? But this one, we have to talk quite a bit. All right, Huckle's rule. The number of pi electrons must follow for n plus 2 pi electrons, where n is whole number. That has nothing to do with number of carbons, has nothing to do with number of electrons. N has to be just whole number 0, 1, 2, and 3, blah, blah, blah. Okay. Now, if n is 0, put 0 right here. For n plus 2 is 2. If n is 1, put 1 right here. 4 times 1 is 4, plus 2 is 6. That's 6. If put 2 in here, 4 times 2 is 8. 8 plus 2 is 10. So basically we have 2, 6, 10, 14, 18, 22, and so on. Now look at down here. Okay, which one have the number of pi electrons follow 4 n plus 2? Well, 6, 10, and 14. Okay, so these are aromatic, the rest are not. Well, the question is why 4n plus 2? I'm going to give you explanation right here. All right, go back to here. A benzene ring, 6 atomic orbitals, 6p orbitals. How many molecular orbitals do we have? Well, if they combine them, overlap all of them, you should have 6 molecular orbitals. Okay, down here is called bonding molecular orbitals. Up here we call anti-bonding molecular orbitals. All right, where is the HOMO? Let's think about that. How many pi electrons are there in a benzene ring? Well, we have 6. 1, 2, 3, 4, 5, 6. Now put down here into MOs. All right, so start with side 1, 1 and 2, and go to 2 and 3. So 2, 3, 4. I said wrong. 1, 2, 3, 4, 5, and 6. Okay. Now that's the HOMO, right? That up here is a HOMO. But now I'm not going to use the word HOMO in this case because we're not doing a reaction. I'm going to use the word where is the valence shell. Remember the word valence shell? What is valence shell? Valence shell is the outermost orbitals. Okay, I mean outermost occupied orbitals. So which one though? Well, the energy level goes from here. This is low up to high. Okay, this is low energy level, high energy level. The outermost energy that are occupied by electrons are right here. This is valence shell. And at the moment, this benzene ring have a closed valence shell, which means that all the electrons are paired up. No single electrons, basically. Okay, and this contribute to the stabilization energy of a benzene ring. All right. I mentioned earlier why aromatic compound must be in a cyclic compound. When it becomes cyclic, you have the molecular orbitals like this. Okay. Once you have molecular orbital like this, it allows that compound to have a closed shell electron configuration. Thus, it must be in a cyclic compound, basically. All right. And this state very stable. Now, this is an example of stable compound. Now, let's take a look at the non-stable compounds. Take a look right here. All right. We have a cyclobutadiene. All right. So 4 atomic orbitals, you get 4 molecular orbitals look like this. We have bonding MOs, we call non-bonding MOs, and we have anti-bonding MOs. You don't have to know all of this. Okay. All right. Let's do this. 4 electrons. Okay. 4 pi electrons. Where is the valence shell? Well, let's go 4. We start with the bottom, side 1, right? 1 and 2. Go to side 2 and 3. So we go 2 and 1, 2, 3, and 4. That is the valence shell. And you can see in this case, the valence shells is an open shell, which means that you have these 2 electrons are not paired. These are reactive. Okay, we call cyclobutadiene an anti-aromatic compound. All right. Now you might have a question: how come the molecular orbitals benzene are not like what we have seen in tetraene, hexatetraene, butadiene? It just like go up in a column. You have like here, here, and here, same energy level, same energy level. We have the type 6, not line up single file like in hexatetraene. Okay, or butadiene is not going up like butadiene. This is cyclobutadiene. You have here, here, and here. I mean, it's different shape basically. How come though? Well, the answer is it's a lot of math, and I don't want to explain a lot of math stuff in this class. Here's what we're gonna do. We're gonna move on to the next video, and I'll explain you without using math. Is that cool?